Greetings from the sub-ether. This is Alan once again with another quick extended color basic video, this time covering a little used command in basic called VARPTR, variable pointer, and how it relates to what we're going to look at with the get and put high-res graphics commands. First, VARPTR shows the location in memory where a variable exists. Let's do an example here. Say I start out and I make a variable called A, and I set it to 0. If I print the VARPTR of A, it says this variable is located at memory location 9733. Well, I happen to know that 9733 and the 4 bytes after it, 5 bytes total, is going to be what makes up the variable A. So let's do a test for I equals 9733 to 9733 plus 4. That gives us 5 bytes. We're going to print I, comma, peak of I, and do next. So those 5 bytes are all zeros because A is 0. Well, let's set A to the number of 1 and do it again. Let's make sure it's still in the same place, variable pointer of A, for I equals 9733 to 9733 plus 4, print I, comma, peak I, next. And you'll see now it says 1290000. And you'll notice that it's not a pattern like you might expect because these are floating point numbers. Remember, A can also be 12.34. And they are represented as some type of floating point where a certain number of bits represent the mantissa and all these different things. You can go to the Wikipedia page on floating point and figure out how it works, then explain it to me. But those 5 bytes represent the actual variable A. So if I print variable pointer, let's clear the variables. I'm going to say A equals 1 and B equals 2. Print the variable pointer of A. Print the variable pointer of B. And it should be right after it. Now you're going to notice that the difference between 9733 and 9740, it actually looks like it went up not by 5, but by 7. And I believe what's going on is the index actually has the variable's name. I'm not sure if that's true. Let's take a quick look. Let's peek at the byte right before 9740. So we'll go back 1. I think that's going to be a 0. Let's look at the one right before that one, 2. That's a 66. Print character string 66. That's a B. So in memory, it looks like this. You've got 1, 2, 3, 4, 5, 6, 7 bytes representing the variable. And the first 2 is the name of the variable, such as A, and then the bytes that represent the value. Remember that variables can be A equals 1. You can have 2 letters, but you can't go more than that. It can be A to Z. You can have AA to ZZ, any combination, and you can put a number after it, like A0 through A9, all the way up to Z0 through Z9. Those are your variables. So there's 2 characters for the variable name, followed by the 5 bytes that make up that numeric variable. Why is this important? Well, you can also look at the contents of an array. So let me clear. If I did a dimension of X and said I wanted to hold 9 items, actually that's 10, 0 through 9, and I printed the variable pointer of X, well, that doesn't work because there is no normal X. You can have X and an array of X. You have to print variable pointer of X and then which element you want. 0. Print variable pointer of X sub 1. Notice it's 5 bytes higher. Print variable pointer of X sub 2, and so on. All of the elements in the array are packed together. Each one takes 5 bytes. So when you declare an array of 10 elements, you know it's going to at least take 50 bytes for the actual 50 numbers, plus the overhead for the variable name and some other index stuff that happens when you have an array, like the size of the array, because you can also have a multi-dimension array like position 10, 10. Now you've got 10 X and Y coordinates, or you could do 1, 2, 3, 4. You could do a 4-dimension array. And so there's a little header above these in memory that will have like, oh, it's 4 dimensions, and the first one has 1 element, 2, 3, 4, and so on. But we don't see that. Variable pointer just returns the start of the actual variable data itself. And I know because an array is packed together, if I have something like dim X of 100, I could start at wherever variable pointer of 0 of x sub 0 is. And that, and then in this case, there's 101 elements, 0 through 100. I would go to wherever that variable pointer is. Oops, see what I did wrong? Why did that work? VARPTR x sub 0. There we go. The reason that works is because BASIC will let you have things that look like long variable names. For instance, I could have bacon equals 1, print bacon. But it only looks at the first two letters. So if I have bacon and eggs equals 2, I can print bacon and eggs. Looks like it's working, but if you try to print bacon, it's 2, because it's really only doing BA. So when I mistype VARPTR as PRT, whoops, VARPRT, well, that's a variable called VA. Oops, VARPRT. There you go. So that's why that command didn't work. Anyway, so my point is, if once you have the location of where an array is in memory, if you know how big the array is, all the bytes after it, 5, 5, 5, 5 in segments of 5, represent the numeric values in that numeric array. Why do we care? Well, here's why we care. I'm going to load this program, and in an earlier video I talked about the high-res graphics modes. I'm going to load this, and it's going to go into a P mode 0 screen. That's 128 by 96, and it's going to draw a box from 00 to 3131. Although the code is trying to draw what looks like 32 by 32, in this mode it's really 16 pixels by 16 pixels, because BASIC always uses the resolution of 256 by 192, then it scales it to fit whatever graphic resolution you're actually on. So somewhere in memory is the graphics data for this video RAM, and also this box in the left corner of it. And I happen to know where that is. The screen starts at 1024 and goes to memory location 1535. Because if you poke 1535 comma some value, you'll see it down here in the bottom right corner of the screen. So there's 512 bytes for this text screen. And if I was on a cassette system, at location 1536 would be the high-res graphics screen. But if you're on a disk system, at location 1536, there's 2K of disk variables. So the real location of graphics memory is 3584. That's 2K after this. So 3584, that's the memory location where the graphics were just drawn. And I could demonstrate that by saying location equals 3584 to, I don't know, let's just say 3600, print peak location. Next, we'll just start printing these across the screen. You're going to see the first 2 bytes were 255s, then a bunch of zeros, then we started seeing the 128. This is actually, these bytes up to this 0 is the first line of the graphics screen, 16 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that's the first byte of the next. How do we know that? Well, there's 8 bits per byte times 16. There's our 128 resolution. So it's 128 pixels across the screen. The first 8 bytes represent the first 128 pixels on the screen. So let's go back to that. This is memory location 3584, and it has 16 pixels that are turned on, followed by the rest that are turned off. Then a pixel in each one of these bytes, and a pixel in each one of these bytes, and so on. So I'm going to go to the next part of the program, which is going to start dumping the bit pattern of the first 2 bytes of each line of the screen. So this very first row of 11111, that's memory location 3584. This is 85, and so on. And this is the start of the next line. You notice the 1s are those set pixels. So this is 2 bytes across, which is 16 pixels, and it's 16 down. That means it's 16 tall. And you'll see the 1 bit is set all the way down these rows, and the high bit is set here, and the low bit is set here. And you can see the square made out of these 1s and the zeros. And over here I print what those values are, so we can identify them in just a moment. 255, 255, these first 2 bytes have all the bits set, that's 255. This one only has the high bit set. The bits are numbered 1, 2, 4, 8, 16, 32, 64, 128. They double. And this one is a 1. So there's a 128 and 1 all the way down. 255, 255. That is what is in graphics memory. Now the next thing I'm going to do is I'm going to declare an array called BX, and it's going to be big enough to hold 7 entries. So I'm going to hit a key, and it is just declared variable pointer BX sub 6. And then I printed where that was in memory. It lives at 10508. It's got to be way after the basic code that I've got loaded in that's doing all this. That's why it's such a higher number from my earlier examples. So BX sub 0 begins at 1058. The next thing I'm going to do is I'm going to do a get from 00 to 3131 into this BX variable. This is, see my last video for what that looks like. I'm going to do a get, then I'm going to print the location of BX again. After the get, notice the location moved. BASIC relocated the BX variable for some reason. And how far did it move it? 10508. You've got 9, 10, 11, 12, 13, 14, 15. 2 bytes plus 5. So there's 7 bytes of overhead for this array as soon as I did the get. That is some data that's being used by something in BASIC, but we don't know. All you need to know is if you get the variable pointer of an array, then use get on that variable to store it in the array. Don't rely on the location of that variable. You gotta update it again. That's something I did not realize. So BASIC put 7 bytes of data in front of, probably, the graphics, the numeric buffer data inside this array, and then it moved the data area down. So inside this BX sub 0 through 6, 0, 1, 2, 3, 4, 5, 6, are the contents of this screen memory. Let's see if it looks familiar. The new variable location was 10515, and here's the bytes. 255, 255, 128, 1. It's exactly the data that was on the screen. So when we get something, it uses the bytes of the array to copy the screen graphics memory directly into it. Now with that in mind, let's take a quick look at something and see what happens. This is probably where the video is going to break down. I'm going to alter where I draw the box. And I'm going to start at 1. And I'm going to go to 32. So I'm just going to shift it over by 1 pixel. Whoops, I didn't see that. Oops, break, break, break. I should really get rid of the rest of the code in here. Oh, right. Because I'm half resolution, I have to go up by 2. Otherwise, I won't see it move. Oops. Ah, what am I doing? 33. Let's try that. And we'll just end after that. Okay, now you see I've shifted to the screen 1 pixel over. Okay, let's run it again. Now let's look at what that video memory looks like. You're going to notice the first 2 bytes, there's a 0 here because I shifted over by 1 pixel. So if I were to get 0 to 31, I would not get the whole box. So I need to move my get over as well. So my data is different. But I'm only looking at 2 bytes here. I should really dump the third, but I think you get the idea. So if I were to get it and then put it back, you're going to see I get the same data here. But that's not what we're going to do. Let's go look at this program, and let's change the get to be 2 through 33, like that. So it's going to try to get the data and move it over. Let's see if it matches. We get it, and we do a 127 and 255. So we're going to look for the numbers 127, 255, 64. Function call error in 250. Because we're not on a byte boundary, we can't get it like that. So we put comma G, so it uses the full quality of the graphics according to the manual. We don't know what that means. We're going to find out in just a moment. Again, we're looking for 127, 255, and 64. We're looking for those familiar numbers. Bad subscript in 260. What's going on? Something's happened. Whoops. Well, we have a problem. we now have a variable that seems to be wrong. Something got messed up when I did that get into the array. Now we're going to cheat a little bit. I'm just going to increase the buffer space. Let's dump it again. Still bad subscript area. Do I even have a BX sub 0? I don't. So what happened? We have something that got corrupt by what I just did. That comma G is expecting something different. The normal get and put seem to be working just fine this way if they're even byte aligned. But this being off by 1 and using comma G, that has changed how it's putting stuff in memory. So we're going to cheat a little bit. We're going to look at where that variable is in memory for BX, 10511. Then we're going to error. We tried to do a get and we couldn't. The location is gone. But the get did not error out. So let's just take a look at 10511. And we'll just go to 10600, print peak I. Let's see what's there. Well, you'll see there's 1, 2, 3, 4, 5, 6, 7. There's those 7 bytes at front. And if you look at the data, 255, 255, 128.1, 128.1, that really looks like the data is correct. So it looks like it actually copied the actual square that we wanted. But it corrupted this variable when we did that. So now we don't have a variable to even do a variable pointer of. So that's going to be the next mystery, to go further into how this array is being used to store get and put buffers, and also what is going on with comma G and the other things when we put it on the screen. So that's just a little quick look at variables and how they're stored in memory, and what get is doing when it's copying bytes from screen memory directly into bytes for an array. We'll look at this in a future installment. Until next time, don't panic.